Good morning, everyone. Here we go again in this spectacular room, but for different kind of party. For deep diving into SQL Server Plan Cache. So I bet you desperately need to deep dive into SQL Server Plan Cache this morning, right? So let's go then. Let's do that. My name is Naumova. I work with SQL Server for, I don't know, a long time. And I'm an MVP, I'm MCM, whatever a certificate is in SQL Server. And I've been working for Microsoft for 5 years, and now I'm building my own consulting company and a training program called SQL Server Master Academy, or SQL Master Academy. So that's all for me. Let's start with the Plan Cache and why I'm here and why I'm deep diving right now in this early morning into the Plan Cache. And that's because you can face a lot of problems because of misconfigurations and misuse of SQL Server Plan Caches. And those problems could manifest themselves in different ways, like simply decrease the throughput in query response time, or even timeouts in query execution or query compilation. So those kind of errors could be very common due to different kind of things or different reasons. But one of them, almost 50% of the cases, is due to Plan Cache mismanagement. So probably you never ask yourself a question, how much Plan Cache do I use in my SQL Server instance, or how SQL Server manages the Plan Cache, or do I have to do something, or SQL Server just manage it by itself? Well, in order to answer all those questions, I will go into the Plan Caches today and will show you how SQL Server deals with that and why it's so important for us to know to have those kind of knowledge in order to check the Plan Cache status and to do some workarounds or to just rewrite the code. But anyway, sometimes or very often you cannot just rewrite your queries, so we have to deal with the plan configuration, or we have to deal with some kind of you have to choose some kind of troubleshooting in order just to release the pressure from the Plan Cache inside SQL Server. So sometimes you can find the signals about Plan Cache problems when you explore wait types. How many of you use waits or wait type troubleshooting in SQL Server? Great. So you know, probably you have faced or you have seen some waits, some typical kind of waits, like CMM thread or resource semaphore query compile. These type of waits are most common waits when you have problems with the Plan Cache, and they are definitely a signal that you have to go and to explore your Plan Cache and to find out where is the problem. Probably there's some Plan Cache bloats, or there's some Plan Cache store growing too much and pressuring the other type of caches inside SQL Server memory. Or you have too much ad-hoc plans, or you have a lot of plans per single stored procedure. So all those problems could be in your SQL Server instance, in case you have seen those kind of waits. By the way, there is a very common issue due to the Plan Cache management which appears in SQL Server 2012 and 2014. Thanks God, they release fix, and we have a fix for that. So you can face a very high CPU usage when you have a hot plan cache in those versions of SQL. But I will talk about this especially this morning, so you will realize that it's not so difficult actually to get a workaround and to fix these kind of issues. So all those issues could be a result of large number of memory pressure events or memory contention problems. And you will end up with a large number of, probably will end up with a very large number of compilation or recompilation per second. So in this way, or these type of problems probably are, as source of those problems could be different than the plan cache. Well, probably, but it's very easy to check the plan cache and to see if there is an issue inside the plan cache and to continue with your troubleshooting efforts. So let's take a step back and start with the plan caching and plan cache mechanism inside SQL Server. So first of all, the plan cache is used in order to save the compilation time. And that's the main purpose of caching actually in SQL Server. So SQL Server has two main caches. First one is the buffer cache, where it stores the data pages that it has read from the disk. And in this way, it will reduce the amount of I/O operations that goes through with the disk subsystem. And the second cache inside the SQL Server memory is the plan cache, when SQL Server stores already compiled execution plans. So in this way, it will save the time and resources when you send the same statement, probably with different parameters, next time. So it will find the plan in cache, and it will use the same execution plan with a different context and different number of parameters, and different value of parameters. So plan caching is something good. And when we have enough plans, when we have a lot of plans in plan caching, it's not something bad actually. It's bad when the plan cache grows a lot and it takes a lot amount of space, and it takes the space from the buffer pool. So all those caches are fluid. When you grow the buffer pool, then you just shrink the plan cache and vice versa. So it's very, very important to get this system balance. And the first and the very important task you should do is to configure the max server memory, because it's the top, it's the border above which SQL Server cannot grow its plan caches and everything else that it's placed in memory. So first of all, we have to put this kind of threshold to SQL Server in order to get those caches fluid inside the memory and to get the SQL Server eventually balance the signs between them. So SQL Server starts caching plans since, I don't know, since SQL Server 7.0 probably, even earlier. But in SQL Server 7.0, it started cache everything, even an ad-hoc plans. Before that, we knew this area of SQL Server memory as procedure cache because we had just procedures execution plan of the procedure cached in memory. So we even had a configuration value to specify the amount of procedure cache. So starting from 7.0, we don't have such an option. The caches are fluid, and we just have a max server memory as a mechanism to control the maximum size of the plan cache and the buffer pool also. So we have to use that. Okay, so what kind of objects we have in the plan cache, how they go there, and what we can do about that. So it's definitely very important to know how the plan cache is growing and what kind of object and what kind of information we can get from the plan cache in order to know our workload. So what kind of queries our developer sends to our SQL Server, or what kind of store procedures do we have, or do we have something that we should take care of according to our plan cache usage. So let's start exploring the plan cache. And first of all, we use dmexec cached plans. This is a common DMV that you can use on your system, but be careful because it could return a huge amount of rows, especially if you have a very large plan cache. So sometimes it's better to use just transaction isolation level written committed, just in order to reduce the workload of the cached plans DMV against the cache. So we have such important columns, very important columns that I'm going to use during this presentation. And first is the plan type, and the second is the cache object type. So the plan type is actually the type of the plan that is stored in the cache. So it's a plan type of a stored procedure, a prepared plan, or ad hoc plan, which are common plans that I'm going to describe here. And we can have an object type, which is a compiled plan, or, for example, a parse tree. A parse tree is something that Query Optimizer builds when you send a query against the view. So it has to unbound the view, and it builds the parse tree, and the parse tree is stored in a separate area of the plan cache. So sometimes this area could become hot or large enough, and that's because you use a lot of nested views. So if you use a lot of nested views, then SQL Server has to unbound all of them and to build a large statement and a large parse tree. So the next kind of object is a typical one, which is an extended procedure, and those are just DLLs like SP-execute SQL, like SP-trace, or something like that, that we use during the workload. So there are also different kind of other objects, but I'm not talking about everything, of course, but the most typical kind of them. So let's start with most common statement for clearing the plan cache. So I'm going to talk about clearing the plan cache later, so don't take this as an advice to execute on our production system. Just hold on, and I will talk about this later. So I'm going to send some queries to SQL Server as an ad hoc query. Ad hoc query means that the parameter, the value is a literal one, so I'm sending the literals to SQL Server, and SQL Server will not reuse the execution plan, and it just compiles and stores inside the plan cache. So probably your next question will be, why SQL Server stores the plan into the plan cache when it is sure, or at least 90% sure, that it will not reuse this kind of plan? Well, I don't know, one of those things. So these are two queries with just different values for customer ID. It's a very simple query, and a dynamic SQL query, wherever, I haven't marked everything. So it's always dynamic SQL. When you send this kind of query as a dynamic SQL, it is always treated as an ad hoc query. So it never reuse the execution plan. So let's see what we got into the procedure cache. So first of all, we got two different plans for every value of the customer ID. So the plans are ad hoc plans and the use count of those plans is 1. So when the use count is 1, or when you query your plan cache with the filter use count 1, then you got all those ad hoc plans that are never being reused. So those plans take memory, 16K, 16 kilobytes for this simple query execution plan. So imagine that you send a huge amount of queries, and your queries are relatively complex, and they generate a lot of execution plans, and the execution plan is not just 16 Ks. Then you get a really high amount of memory wasted because those kind of execution plans are not going to be reused. So this is your first problem, and we have this query also that is part of that has been sent as an execute statement with dynamic SQL. This is also an ad hoc query, and the use count is 1. So SQL Server sometimes tries to parameterize some queries, but this is not with a good success. I mean, we can do that. I will show you how the SQL Server does that. For example, I'm sending this kind of query, and I'm sending this kind of query, which is almost the same, but with different value of sales order ID column as a filter, and there are some spaces or enter symbols inside the text. Why it's so important, you'll see later. So let's see what we got. So SQL Server actually tries to parameterize this query. Here we go. And we have a prepared type of compiled plan which has been reused 2 times. So here is your parameterized plan, and it takes such amount of memory. And here are the shell queries, so-called shell queries, which are just text. This is not the whole plan, but just text with a pointer where the overall plan inside the cache is stored. So why SQL Server managed to parameterize this type of query, but not the query that I've sent first? Well, the difference is that the sales order ID is the primary key of my table. So when I put the filter sales order ID equals to some value, then SQL Server considers this as a safe plan. So whenever value I send as sales order ID, I always get a same execution plan, and it's absolutely safe for SQL Server to parameterize and to have this single execution plan whenever values I send to sales order ID. But there is some caveats here. Actually, it realizes, or it brings the integer as a parameter type, and when I send this kind of value, then, then I will get, guess what? Yet another execution plan, again parameterized one, but with a parameter type of tiny integer. And when SQL Server makes auto-parameterization, then it just reads the value, not the column type of the column in the table. So in this case, it's absolutely no guarantee that you will end up with the same execution plan every time you send this query to SQL Server. So beside that, there are really huge amount, a long list of restrictions for auto-parameterization inside SQL Server. Like, SQL Server does not parameterize query with join, with group by, with some aggregations, or with some calculations, etc. So there is a huge amount of limitations for doing such a plan reuse because of auto-parameterization. So this is not a solution for our ad hoc query problems. So You can do a forced parameterization on the database level as a database option, but it's still not a solution because you can end up with a huge problem like parameter sniffing, for example. So something that you could do is to optimize for ad hoc or to reduce the amount of memory that SQL Server uses in order to store the ad hoc plans. Instead of storing the whole plan, you can use the optimize for ad hoc, and SQL Server will store just the plan stub, which is just a pointer or a text of your query in order to match the query text in case you send the same query next time. And when you send it next time, then SQL Server will compile and save the overall plan. So in this case, you can optimize your plan cache usage according to the plan cache size. So this is the way it works. So I'm sending 2 queries, and I'm going to show you how much space the execution plan will take. So instead of saving the whole plan, then SQL Server stores just the compiled plan stub, and this is still an ad hoc plan, but it takes just 128 bytes instead of 16 kilobytes. So you can save a lot of memory with these particular settings, and it's a highly recommended one for setting to your SQL Server environment. So the parameterized statements, this is actually the second thing you should do in your SQL Server production environment, just to allow optimization for ad hoc statements and ad hoc plans. So when you send a parameterized query like sp-execute SQL, and when I change just a parameter here, I end up with a parameterized type of plan cache or of execution plan. But this time, I don't have such additional shell queries like in auto-parameterization, and I have an additional proc of type extend proc and sp-execute SQL, which takes about 8K of memory. So this is the way sp-execute SQL works. So it's a good way to parameterize your queries, but still, if you don't specify the parameter type, which is here, you will end up with an ad hoc queries again. So what kind of structures are store procedure execution plan? When you send the execution of a store procedure inside SQL Server, then you will have a store procedure plan, which is a proc plan, which is a proc compiled plan. And I'm going to show you this type of object that goes into the procedure cache. And the compilation is performed during the first store procedure execution. So when the store procedure executes for the first time, then the query processor compiles the store procedure and puts the plan and saves the plan into the plan cache. So in this way, we have a proc compiled plan. Here we go. And this is our store procedure text. So the store procedural plans takes much more as a size, but it will be reused when you execute the store procedure next time. So use counts of store procedure is usually much larger than 1. So your store procedure is important for your store procedure to be saved and to be kept into the plan cache, because the compilation is avoided next time you execute your store procedure. So what kind of objects and what kind of information could I get from the plan cache. So there, beside all those objects, there are dependent objects that are stored during the execution of the plan, of the execution plan. Like executable plan, like plan attributes, like execution statement or execution data for a particular stored procedure execution. So, for example, when you query with a function, with a cross-apply with a function plan-dependent object for a particular plan handle, then you can get an executable plan as a dependency object inside the cache. So dependency objects are relatively light in size, relatively small in size, not like the overall execution plan, and they are relatively cheaper to be recreated if needed into the plan cache. So there is something important according to this store procedure, and when I got this store procedure, and its plan handle is actually the plan GUID for the procedure, for the specific procedure. Then I can get the plan attributes. So the plan attributes are something specific to the execution plan. There are a lot of them, as you can see. I'm not going through them. But there is a column called is cache key. So some particular attributes are included into the plan cache key. And when you execute a store procedure with the same value of all those attributes that are part of the cache key, then you will have the same execution plan. But if at least one value of the attributes is different for the next execution of your store procedure, then a new execution plan will be generated for this particular store procedure with a new cache key. So cache key is important because SQL Server uses the cache key for searching the procedure plan for this particular execution plan, for finding this plan. So the cache key is something that is really important, and when you have this kind of situation, for example, I will change the language ID, which is part of the cache key. Then, here we go. I don't have a clue what it said. But anyway, I'm going to execute, oh, sorry. It's better to be in the right database. So when I query again my procedure cache, then guess what? I will have another execution plan which take the same amount of size, you know? So this is your second problem that you can get into the plan cache. So doubling the plans, the execution plans for the same object, for the same stored procedures. And this is because you can have a different, you send the stored procedure execution with the different set options, or with a different language, or a different date format, or, for example, you have a specific name resolution process that is different for different execution of the same stored procedure. Like, for example, you don't specify as part of the objects the name of the schema. When you don't specify the name of the schema as part of the table reference, then SQL Server has to deal with the name resolution. And when you get different users inside the database, when you execute the stored procedure with the different users, database users, then for every user it will generate a separate stored procedure execution plan. This could be a really very expensive for your plan cache, and this could waste a lot of space into the plan cache. So thanks God it's relatively easy just to find all those procedures with the same object ID and to find out that you have these kind of problems. So generally said, a store procedure should have one or two execution plans in memory. When you have a lot of them for the same object, then you will waste space, and they will be very difficult and very slowly for SQL Server to find the particular plan of this store procedure in cache, because there are a lot of them. Okay, so this is a second thing that you should care about. And okay, so let's talk about plan cache stores, so where all those objects are stored, actually. And what is important according to the size management, store size management. So what are thresholds and how we and when we get a memory pressure event, either internally or externally. And what is going on inside SQL Server when there is a memory pressure event. So there are four cache stores that store plan caches. Execution plans, sorry. So object plan store stores store procedures and functions. Execution plan of store procedures and functions. SQL plans, guess what? This is the hottest of the cache stores, and it stores execution plans of the ad-hoc statement. Ad-hoc and parameterized statement execution plans are stored in SQL plans cache store. So it needs a special attention in your SQL Server instance. Bound trees is the plan cache store that stores a parse tree. So it is the parse tree that is generated from views when you send a query to view. So when the bound tree goes up or goes larger, then you have to find out what kind of views or how many views you reference in your code, or what kind of nested level do you have in your views. So extended store procedure is a relatively small cache store, and you generally don't have any problems or don't face problems with this kind of cache store. So you can use those kind of views, dynamic management views, to find out what is the size for a particular cache store and how many objects SQL Server stores in that particular cache store. So let's do that. So when you use the well-known DMV DMExec cache plans, then you can get the number of plans and the size in megabytes, but this is by plan type. But you have to match all those plans in the particular cache store, and that's why I'm using the memory cache counters. So there are a lot of stores, by the way, in SQL Server, about 125, but we do care mostly of those that stores plans. So here we go. Those two cache stores plan. And this is the way I can find how many entries I have in a particular cache store and what size the particular cache store has. Why is that so important? That's because there are thresholds. There are magical numbers inside SQL Server, and when you get them, you have problems. So what are the magical numbers here inside the cache store? So the size of the cache is tracked per particular cache store for a particular cache store. So we don't care about the overall plan cache generally. We care about the size of particular cache store. So what are the numbers? So the magical numbers generally change through the versions. And the major change was in SQL Server 2005. And when they realized in RTM that the planned cache, the single cache store, can take almost 50% of SQL Server memory. The single cache store, you can imagine. So the calculation of the planned cache size of the single cache store was made with different formulas throughout the versions. So in SQL Server 2005, we had 75% of memory from 0 to 8, 50% of visible target memory from 8 to 64, and 25% of visible target above 64 gigabytes. So what is the visible target memory? Actually, the visible memory is the memory that is part of the SQL Server process. So in 64-bit system, it's practically unlimited. But if you have a max server memory configured, then you have a target server memory. Okay? So either you have all physical memory on the box as a target server memory, or max server memory if you have configured it properly. So this is why it's important to configure max server memory, by the way, because if you don't configure it, the SQL Server will try to get all the memory from the box. And when it tries to allocate and commit the memory, all the physical memory, then at some moment of time, it will contend with the operating system, of course. And they will be in conflict with each other just for releasing a memory. So those are two examples of calculating the cache store pressure limit. Why so important? Because the cache store pressure limit is the value that is calculated inside SQL Server, and when you reach this value per particular cache store, then SQL Server indicates or raises memory pressure event. And when the memory pressure event is escalated, then a specific algorithm takes place and starts to remove plans from cache. So they realized that the calculation of this cache store pressure limit value in SQL Server 2005 is something that is not very well done. And they changed this in SQL Server 2005 Service Pack 1. And from Service Pack 2, actually, there is a different formula for calculation, and there is more restrictive threshold for single cache store. So, for example, you have a 75% of 4 gigs up to from 0 to 4, which is the first difference, plus 10% instead of 15 from 4 to 64 gigabytes, and 5% above 64 gigabytes. So, for example, if you have a 28 gigabytes target memory for SQL Server 2012 or 2014, it's not changed. Since then, according to this formula, you will have a cache store pressure limit value of 5.4 gigabytes. What does it mean? When you get 62.5% of this cache store pressure limit, meaning when your particular cache store reaches, in this example, 3.375 gigs, then it will escalate, it will raise the local memory pressure event because of growing of this particular cache store. Why exactly this value? Why 62.5? Well, those magical numbers inside SQL Server. Actually, before SQL Server 2012, we had a single page allocation and multiple page allocation, right, inside a memory model. So we had this 70% or 75% of single page allocation and 50% of multi-page allocation as a threshold for cache store size. Now we had an average of that as a value, as a percentage. So In case you reach that, then SQL Server will have a local memory pressure event, or you can have a global memory pressure event, which could be an external global memory pressure from the operating system, which is actually the case when SQL Server has a contention with the operating system, case when you haven't configured the max server memory, for example. Then they start to compete for memory at a specific point of time, at a specific amount of memory. And SQL Server gets a memory pressure from the operating system, and it starts to remove the plans from cache. And it is considered as a general memory pressure event because it is executed against all caches inside SQL Server, not just a specific cache store. So it is something that you can face at a huge delay in response time of SQL Server because it takes a time to remove or to reallocate pages from the memory inside the buffer pool, like database pages, like lazy writer process is working, and inside the plan caches, like eviction policy algorithm, which removes plans from cache. So there is an internal global memory pressure that is also connected to some specific calculations inside SQL Server, like when SQL Server calculates that every possible cache store will grow in totally of 80% of planned cache pressure limit, then it escalates the internal global memory pressure. So what is the SQL Server reaction in this case? So the SQL Server reaction on memory pressure is to start the eviction policy algorithm. So eviction policy algorithm is something that is not so bad because it just releases memory. It removes plans from cache. But the problem is that when it starts removing plans from cache, it executes that on the same thread of the query that actually escalates or gets the threshold. And in this particular occurrence of the eviction policy algorithm start, then execution, then you can face a timeout or query compilation timeouts or query execution timeouts or delays in query execution as all. And this is something that generates a wait type of CMEM threads, actually. CMEM thread wait type is a wait type that is registered when you have such a waiting for the memory, for memory contention to store the object, the execution plan in memory, and to release the execution plans from memory. So the eviction policy algorithm is executed based on cost of the execution plan. So every execution plan has its cost. And the good thing is that ad-hoc plan cost is 0. So the ad-hoc plans are first candidates to be removed from the plan cache in case there is a memory pressure event. One cycle of the eviction policy algorithm removes about 16 entries from the cache. And reduces the cost of other objects in the cache by half. That's why it takes several cycles to reduce the memory that is used by the particular plan cache or cache store. And that is why you feel like SQL Server does not release memory fast. And that's because it does this in cycles. So, thanks God it does this in this way, because if it does this immediately, then probably, well, I couldn't predict what will be as a performance or as a process. So, for a different kind of execution plans, there are different kind of costing. I mean, ad-hoc plans cost 0, but other type of plans cost as much as resources they take to be compiled and saved into the memory. So the cost is formed by the amount of I/O operation that are included in the execution plan. The cost is formed by the context switches and the memory that the plan takes to execute. So when the eviction policy algorithm executes throughout the plans, it reduces the cost of plans by half. And next time, on the next cycle, when the plan is gets cheaper, it will be eventually removed from the cache. So let's see some specific issues or specific DMVs or information that you can get from the plan cache in order to find out if there is an issue with the memory pressure. First of all, you can get your cache plan entries using this DMV. So the MOS memory cache entries has an entry for every object, and every object that is stored in particular cache store. So if there are a lot of columns here, and I'm going to filter this and to specify this in order to be clear. So you can get the total amount of entries by grouping and counting against the memory cache entries. But if I get a cache plan and memory cache entries, then I can get the costs of your execution plans. So these are the use counts, these are the size in bytes that you already know, and those are columns, actually, that forms the cost of the plan. So there is an original cost of the plan, and there is a current cost of the plan. And guess what? If you have started an eviction policy algorithm, automatically by SQL Server, of course, then you will have a difference between the current cost and the original cost. And that could be a signal that you faced a memory pressure events for particular execution, for particular cache store. So this is the first place that you can check. The second one is a clock hand. So the clock hand registers those cycles of eviction policy algorithm and register all the execution plan that has been removed since the last cycles has been started. So here I have object plans, cache object store, external or internal memory pressure, and the clock hand respectively, and the clock hand for SQL plan cache store. So these are 0 right now on my laptop, but I will show you something as a performance report when I catch these memory issues and memory pressure event, and for you to see how it looks like. So please don't read the text. Okay, so first of all, the customer has had this memory issue. So if you get the memory available megabytes is really below the acceptable value. So the max server memory has not been configured in for this SQL Server instance. It was left by default. And the SQL Server instance was competing with the operating system to get the memory. And the memory was less than 5% all the time, which actually generated the hand external and row count cycles of SQL Server eviction policy algorithm. So in this case, a lot of cycles has been executed inside the plan cache, and a lot of objects has been removed from the plan cache because of that. And another signal of external or internal memory pressure is this ring buffer resource monitor. So ring buffer resource monitor, I'm going to show you. From ring buffers. So there is an indicator if there is currently a memory pressure into the plan caches, and when the memory pressure is external, then the indicator system node is a value of 2, and if it is internal, then the indicator process node has a value of 2. And here I have these indicators of indicator system node and indicator process node. So there is definitely a currently memory pressure event, and currently during the catching of all those DMVs, the customer faced huge amount of plans that has been removed from memory, and part of the plans were even store procedure plans, and they have faced these CMM threat weights and everything that is connected to the plan cache mismanagement issues. Okay, so there is another, by the way, there is another threshold, and that actually brings the memory pressure event. It's not just the size of the particular cache store, but the number of plans in that particular cache store. So, as a side note, let me show you what I mean, actually. So, when SQL Server has to find a plan in cache, then it has to go through the hash tables. So every cache store has its own hash tables. So the number of hash tables inside the cache store is a fixed value. And when the number of buckets in the hash store is a fixed value, sorry. So every cache store has its hash table, and the hash table stores particular number of buckets, and in every bucket there are execution plans. So how SQL Server stores and finds the plan in cache? So every plan has a bucket ID. And when it goes, this bucket ID is actually formed by a specific formula that contains the object ID and the database ID. And when you have one execution plan per object, then it's easy for SQL Server to find and it's relatively fast for SQL Server to find that particular execution plan. But when you have a lot of plans per particular object, then SQL Server has to compare every value of the cache key for that plan except bucket ID in order to find the particular plan in cache, which could be slower, relatively slower. So we have a fixed amount of buckets for every cache store, and the fixed amount of buckets is this. So object plan and SQL plan has this amount of buckets, and you have a limit of number of plans that could be stored in a particular cache store. The limit is 4 times number of buckets into the cache store, which is 160,000 plans in a specific cache store. And guess what? If you have a lot of ad-hocs and you have enabled and optimized for ad-hoc, then inside the SQL plan cache store, you can get a lot of ad-hoc plans because they are small in size, right? And you can get this, you can reach this threshold in a less amount of space that cache store has been reached. So this is something that appears as a problem when you have a huge amount of ad hoc plans, particularly in the SQL plan cache store from SQL Server 2008 and above. And that's because they enabled optimize for ad hoc setting from SQL Server 2008. So when you reach this amount of plans, then you will just face a memory pressure event. So plans have to be removed from memory. But in SQL Server 2012 and SQL Server 2014, this removal from the plan cache will take a lot of CPU resources. So it will take a spin lock, a high amount of spin locks. And they built a fix for that. So the fix is in this KB. So the fix is enabled when you, is working when you install those service packs and cumulative updates, and also you can apply the change with this trace flag. Of course, you have to switch and optimize for ad hoc to true, and you also could enable the trace flag 8032, but be careful. This trace flag will return the calculation of the cache store pressure limit to values to the formula that has been in SQL Server 2005. When you get a chance to increase the single plan cache store to almost half of size of memory. So it's a very dangerous, actually, you could do that, but it's really dangerous. So you have to assess if this is really a solution for you. Actually, if this is not a solution for you, there could be an easier solution, and an easier solution is just to clear the cache. That's as simple as that, on a periodic basis. But, sorry for this, but you have to clear just the cache that stores the ad hoc plans. So you can check the cache size, and you can just execute DBCC free system cache with SQL plans. This will clear your ad hoc plans from the cache and will release the pressure. And you better do that before the memory pressure occurs. So when your cache reaches below those thresholds, as a size and as a number of plans. So the logic is actually clear. It's not something like a very complex. So as a summary, it's definitely sure that you need to pay attention to the plan cache. And that's because all those problems that I have mentioned during this session. So before that, even before that, you can switch optimize for ad hoc to true. It's always good to do that. And as a second thing, you have to configure the max server memory setting. You can monitor after that the usage of the plan cache. And you can find out if you have this kind of situation or this kind of problems, a lot of ad hoc plans and or a lot of plans for a particular object. Either because you have a different settings or a different cache key for a particular object, or if you have a need for SQL Server to perform a complex name resolution process. So if you use 2012 and 2014, then you definitely need to apply the recent service pack. And if needed, if you have these kind of problems, then you definitely will need the cumulative update, the respective cumulative update mentioned in the KB. So be careful with 8032. I'm not suggesting for you to apply this trace flag. Instead of that, it's better to find the problem and to even remove those entries from the cache manually. You have this DBCC free proc cache for the particular plan or for the particular database or the particular object. So you can remove those problematic execution plans from the cache, or to periodically clean the SQL plan cache store, the plan cache store for ad hoc plans. Sometimes it's better than enabling this trace flag, or, of course, you can change your application. So, that's all from me for today. Thank you for your attention, and if you have questions, just please feel free to ask me. I will be around for 5 to 10 minutes. Thank you very much.